Have you ever wondered how machine learning models actually know if they're doing a good job? Today, we're diving deep into one of the most powerful tools in a data scientist's arsenal, the confusion matrix. By the end of this video, you'll not only understand what it is, but you'll be able to read it like a pro and use it to debug your own models. Whether you're a beginner just starting your ML journey or someone looking to solidify your understanding, this video has something for you. So let's jump right in. Let's start with the basics. A confusion matrix is essentially a table that shows how well your classification model is performing. Think of it as a report card for your machine learning model. It's called confusion matrix because it shows us exactly where our model gets confused, which classes it mistakes for others. The beauty lies in its simplicity. It's just a table, but it tells us everything we need to know about our model's performance. For example, if we're building a spam email detector, the confusion matrix will show us exactly how many spam emails were correctly identified, how many legitimate emails were wrongly marked as spam, and vice versa. Let's break down the anatomy of a confusion matrix. We'll start with a binary classification problem where we only have two classes to predict. The matrix has four key components: true positives, TP, cases where we predicted positive and it was actually positive; true negatives, TN, cases where we predicted negative and it was actually negative; false positives, FP, cases where we predicted positive but it was actually negative, also called type 1 error; false negatives, FN, cases where we predicted negative but it was actually positive, also called type 2 error. Let's use a medical example. Imagine we're testing for a disease. True positive, we said disease present and patient actually has the disease. True negative, we said no disease and patient is actually healthy. False positive, we said disease present, but patient is healthy. This might cause unnecessary anxiety. False negative, we said no disease, but patient actually has it. This is potentially dangerous. Now that we know the components, let's learn how to read the matrix effectively. The rows represent the actual true labels, while columns represent our model's predictions. Looking at this example matrix, our model correctly identified 85 positive cases, true positives. It correctly identified 90 negative cases, true negatives, but it incorrectly labeled 10 negative cases as positive, false positives, and it missed 5 positive cases, labeling them as negative, false negatives. We can also view this as percentages or normalize the matrix to better understand the proportions. This is especially useful when dealing with imbalanced datasets. Pro tip: always check if your matrix is normalized by row, column, or shows raw counts. This changes the interpretation completely. Here's where the confusion matrix becomes really powerful. From these four basic components, we can calculate several important metrics. Accuracy. Accuracy equals TP plus TN divided by TP plus TN plus FP plus FN. This tells us the overall correctness of our model. In our example, that's 85 plus 90 divided by 85 plus 90 plus 10 plus 5 equals 92.1%. Precision. Precision equals TP divided by TP plus FP. This answers, of all the positive predictions we made, how many were actually correct? In our case, 85 divided by 85 plus 10 equals 89.5%. Recall, also known as sensitivity. Recall equals TP divided by TP plus FN. This answers, of all the actual positive cases, how many did we correctly identify? Here, 85 divided by 85 plus 5 equals 94.4%. Specificity. Specificity equals Tn divided by Tn plus Fp. This tells us how good we are at identifying negative cases correctly. That's 90 divided by 90 plus 10 equals 90%. F1 score. F1 score equals 2 times precision times recall divided by precision plus recall. This gives us a balanced measure between precision and recall. F1 equals 2 times 0.895 times 0.944 divided by 0.895 plus 0.944 equals 91.9%. Each metric tells us something different about our model's performance, and the best choice depends on your specific use case. So far, we've looked at binary classification, but what about when we have multiple classes? Let's say we're classifying images of cats, dogs, and birds. The same principles apply, but now we have more complexity. Each row still represents actual classes, and each column represents predicted classes. The diagonal elements are our correct predictions. Looking at this matrix, we can see our model is great at identifying cats, 92% accuracy. It sometimes confuses dogs and cats, 8 cases. Bird classification is perfect in this example. For multi-class problems, we calculate precision and recall for each class separately, treating it as a one versus all problem. Then we can average these metrics across all classes. Let's look at a real image classification problem. Here's a confusion matrix from a model trained to classify different types of vehicles. Notice how the model confuses trucks and SUVs more often. This makes intuitive sense as they share similar visual features. Fraud detection. In fraud detection, we care more about recall for fraudulent transactions. We don't want to miss any fraud cases, even if we have some false alarms. Medical diagnosis. In medical applications, the cost of false negatives, missing a disease, is typically much higher than false positives, false alarms, so we optimize accordingly. Common pitfalls and tips. Imbalanced datasets. Be aware of accuracy in imbalanced datasets. If 95% of your data is negative class, a model that always predicts negative will have 95% accuracy, but be completely useless. Choosing the right metric. Always choose metrics that align with your business objective. High precision needed. Email spam detection. Avoid marking important emails as spam. High recall needed. Disease screening. Don't want to miss any cases. Balanced approach. General image classification. Sample size. Make sure your test set is large enough for reliable estimates. Small test sets can give misleading confusion matrices. Let's quickly look at how to create confusion matrices in popular tools. There are also great online calculators and visualization tools if you prefer a no-code approach. And there you have it. You now understand confusion matrices inside and out. Remember, the confusion matrix is more than just a table. It's your window into understanding exactly how your model behaves. Key takeaways. 1. Confusion matrices show you exactly where your model makes mistakes. 2. Different metrics matter for different use cases. 3. Don't rely on accuracy alone, especially with imbalanced data. 4. Use the insights to improve your model iteratively. If this video helped you understand confusion matrices better, give it a thumbs up. And if you want to see more machine learning concepts explained simply, make sure to subscribe and hit that notification bell. What topic should I cover next? Let me know in the comments below. Until next time, keep learning and keep building amazing AI.